All right, here is part 2 of the STAAR Geometry Practice Test answers. Let's start with, we're going to be going 11 through 20 on this one. So number 11 says a conditional statement is given below. If two interior angles of a triangle are acute, then the third interior angle must be obtuse. Which of the following best describes this statement? Well, first of all, if two interior angles of a triangle are acute, that doesn't really tell us much, because if we think about different types of triangles, like a right triangle, well, that has two acute angles. An obtuse triangle, that has two acute angles, if this one was obtuse. Or we could have an acute triangle, where obviously we have three acute angles. So two acute angles doesn't really tell us much about the triangle, because basically all triangles have at least two acute angles. So this part about it saying then the third interior angle must be obtuse, that's not true. So I know it's not going to be either A or C, because this isn't even a true statement. So why is it false? Well, B says the statement is false because the third interior angle must also be acute. That's not true. The third interior angle could be obtuse, or it could be a right one. So then it has to be answer choice D. The statement is false because the third angle could be acute, obtuse, or right. If we move on to the next question. Question 12 here says the side length of the smaller square is 1/3 of the length of a larger square. Which of the following statements describes the area? Okay, so let's say that I have a square of x. Let's make a bigger square. Let's call this x. And this is 1/3 x. So it says the side length of a smaller square is 1/3 the length of a larger square. Which of the following best describes the area? So if I was to find the area, this would be x, and area of a square is base times height, or x squared. And if I found the area of this one, whoops, it would be 1/3 x times 1/3 x. Area equals 1/9 x squared. So then the area does look like it should be 1/9 of the area of the larger square, which makes sense, because if I was to divide this up into thirds, and each one of these was 1/3 x, 1/3 x, 1/3 x, the whole length adds up to 1x, and there are 9 of these squares, so the area is 1/9 as much of the larger square. For question 13, a pattern of dots is shown in the 4 figures below. If the pattern continues, which expression can be used to find the total number of dots? Okay, so we're just using the number of dots here. So in figure 1, it looks like we have 2 dots. Figure 2, we have 1, 2, 3, 4, 5. Here we have 8, 9, 10, 11. So a couple different ways you could do this type of problem is, one, just plug in the figure numbers for n and see if you get the correct number of dots for each one, but you would have to do that. Another way is to see if you can recognize a pattern in what's happening. Are you adding something to each term? Are you multiplying to something to each term? Looks like the difference here is 3 every single time. So it looks like I should be able to multiply another 3 in there another time for each figure. So that being said, A and D jump out to me, because as n increases by 1, I'm going to multiply by 3 another time, and so it'll be the next multiple of 3. So it'll go from 3 to 6 to 9, and then there's some starting point. We might start at -1, we might start at -5, somewhere around there. So I'm going to check these two and plug in and see. So if I plug in at 1, minus 5, I end up getting 3 minus 5 is -4. Are there -4 dots? Nope. So I don't think it's A. If I plug this in here, I get 3 minus 1 is 2. So I do get 2 dots. If I plug it in for the rest of them, I'm just going to jump to. If I jump to this one, figure 4, I should be able to plug in a 4. So 3 times n minus 1, 3 times 4 minus 1, I do get 12 minus 1, or 11. And if I check the other ones, 9 minus 1, I get 8, 6 minus 1, I get 5. So this one does work for all of the figures and the number of dots. For number 14, the equation of a line containing the leg of a right triangle is -4x. So the equation of a line is -4x for a leg of a right triangle. Okay, so that means it's one of these two pieces here. Let's just say it's this one. That means the other leg has to be perpendicular to it. It's not the hypotenuse piece that we're given. We're given one of the legs, and because the legs are the pieces that form the right angle, the other leg has to be the one that's perpendicular. Which of the following equations could represent the line containing the other leg? We just need to have a perpendicular line, which means perpendicular slope. They need to be opposite reciprocals. So if this line has a slope of -4, or -4/1. The reason I wrote it like this is so that we could do the opposite reciprocal. Do the reciprocal, so a perpendicular line is going to be 1/4. So flip the fraction upside down and switch the side. Should have a slope of +1/4. So I see that G does have a slope of +1/4. That will be my answer because those slopes are opposite reciprocals. They're perpendicular to each other. All right. Question 15. Two regular hexagons with center C, apotheosis shown in the figure below. Each vertex of the smaller hexagon is a midpoint of the side. So on this one here, it looks as though we have a few things that we need to do. The easiest way to do this one happens to be with special right triangles, but with any regular polygons, you do have a formula that you often have to use trigonometry. So question 15 says, two regular hexagons with center C and apothems A and B, so those are given the apothems, are shown in the figure below. Each vertex of the smaller hexagon is a midpoint on a side of the larger hexagon. So they just happen to meet at these. A equals 12 square root of 3, and B equals 18. What is the total area of the shaded regions? So the first part is make sure we understand how we're going to approach this one. And once we get a plan of attack is actually writing down the formulas and plugging in the pieces to do this one. So the shaded region, if there was no hexagon in the middle, it would just be the area of the big hexagon. But to make the shaded regions, we're going to have to subtract off the area of the smaller hexagon. So to do that, we're going to start off with a formula that says area is going to equal the big hexagon minus the small hexagon. Okay, so the formula for area of a regular polygon equals 1/2 apothem times perimeter minus 1/2 apothem times perimeter of the smaller hexagon. So the apothems are given, so I could plug both of those in. For the big hexagon is 12 root 3. The apothem of the small one is 18. And I don't know the perimeter there either, so I'm going to have to plug that one in at some point. How do I figure out the perimeter of these? So normally you're given a side of a polygon and then you need to figure out the apothem. Here they give us the apothem and now we need to figure out the sides to get the perimeter so that we can do the area. We do these in the same way. We can actually create congruent isosceles triangles by drawing lines from the center of the hexagons to the vertices. So if I draw this line right here, and here, I create an isosceles triangle that has a base, that's one of the sides, and a height, that is the apothem, and I can use what I know about the angles around the center point to help me figure out angles on a right triangle, and eventually either use special right triangles or trigonometry to solve this one. So if I look at this right triangle right here, I know that the apothem is 12 root 3, so this side right here is 12 square root of 3. If I look at this being a hexagon, I know that I could draw 6 of these isosceles triangles. So if I take the 360 degrees around the center point and divide it by 6, I know that each one of these whole angles here is 60. And if I cut that in half when I draw the apothem, I actually end up with a 30-degree angle on each half of that. So this angle up here is 30 degrees right there. And if I solve for this piece, then I know that the whole side down here, if this is x, the whole thing would end up equaling 2x. So this whole side right here would be 2x. So then all of the sides would be 2x, and times 6, I get 12x. So the perimeter, once I solve for x, is just going to equal that times 12, or 2x times 6. So then I could do this using special right triangles. If I label the sides of this triangle in terms of x from the formula sheet, I know the side opposite of 30 degrees on a 30, 60, 90 special right triangle is x. That's already labeled x. The side opposite of 60 degrees is x square root of 3, and the hypotenuse is 2x, and I don't actually even need to solve for that. But once I have labeled my sides, if I know one of the sides, I just write an equation with that side. So I know that 12 square root of 3 equals x square root of 3, and I can solve for x and that side. So divide both sides by the square root of 3, cancels out. And this one conveniently cancels out, so I actually end up getting x equals 12. So that means 2x, or 2 times 12, will equal 24, or 12 times x equals 144. So the first perimeter here that I just got equals 144. All right. For the other one, I'm going to do the same thing, but now I'm looking at the inside or smaller hexagon. So I'm going to erase a little bit of this and do the same thing here. I'll pick a different color so that we can see it a little bit better. I'm going to need to find the pieces here to help me figure out. I'm going to call this one y this time, and this was 18 if we had it labeled there, the apothem of the smaller hexagon. Let's do the same thing. So if I look at just the right triangle, it's a hexagon, so this big angle here is 60 again. Cut it in half, you get 30 degrees. So this angle once again is 30 degrees. And the leg we're looking for down here is going to help us figure out this piece. Multiply it by 2, we get 2y, or the whole perimeter will be 12y for this one. All right, so same thing. If I label the sides in terms of x, I get x squared of 3, 2x. Write my equation here. X square root of 3 equals 18. Now this one's not going to be quite as easy, but I do the same steps. Square root of 3, square root of 3. I get x equals 18 over square root of 3. If I rationalize the denominator, basically I have a square root symbol in the denominator. I can multiply by a special form of 1, square root of 3 over square root of 3. I end up getting 18 square root of 3 over square root of 3 times square root of 3 is square root of 3 squared. And those are inverse operations, so they cancel out. Square root of 3 squared is just 3. So now I can simplify the 18 over 3 is 6 square root of 3. So that means this side down here, if x is 6 square root of 3, this side is 6 square root of 3. So then that means p equals 12 times 6 square root of 3, or p equals 12 times 6 is 72 square root of 3. Now, looks like our answer choices are exact answers, so I'm not going to plug all of this in the calculator because I need my answer in terms of square root of 3. So I'm just going to multiply the numbers that I can multiply on here, like the 1/2, the 12, and the 144. So 1/2 times 12 times 144. Let's plug those in the calculator, see what we get. And I get 864. Oops, a little bit off the screen there. Looks like I get 864 on there. So I get 864 times square root of 3 minus, same thing, 1/2, 18, and 72. And then I'll leave it as multiplied by root 3. So 1/2, 18, and 72. And I get 648 times square root of 3 for that one. So 648 square root of 3. And when I subtract those, 864 minus 648, I do get 2, what is that, 16? Square root of 3, yep. So 216 square root of 3. And whatever the units are should be square units for area. So what do we have here? Centimeters? Yeah, so centimeters squared. And that looks like answer choice C should be our answer. The other way you could have done this was with trigonometry. You could have set this up using the tangent ratio to solve for this one. So I'll do it one time just so you have that example on there. You could have set up as tangent of an angle 30 degrees equals opposite over adjacent, which would be 18. And you get 18 times tangent 30 equals x. If you multiply both sides by 18, you multiply by 18 over here. And you get approximate values, but you can use that to get the whole perimeter and type it in. And once you get your whole answer as a decimal, then you could just see which one of these values was equivalent to that decimal value you get. So 216 root times square root of 3, whatever decimal you get when you multiply that root 3 should have been the exact answer that you would have gotten here if you used approximate answers from trigonometry. All right, for question 16, 2 conditional statements below are true. Based on these conditional statements, which statement must also be true? So if 3 and 4, angle 3 and angle 4, form a linear pair, then they are supplementary. If angle 3 and angle 4 are supplementary, then angle 3 plus angle 4 equals 180. Okay, so kind of common sense stuff we should know about the definition of linear pair and being supplementary. Based on the conditional statements, which statement must also be true? If angle 3 and angle 4 form a linear pair, then angle 3 plus angle 4 equals 180. Seems reasonable. If angle 3 plus and angle 4 form a linear pair, then angle 3 is 90, 490. We don't know that that's true. You can have plenty of other angles that are linear pairs that don't have to be 90. You could have 180. If angle 3 plus angle 4 equals 180, then they form a linear pair. That's not necessarily true. Just because you have 2 angles that add up to 180 doesn't mean they have to be adjacent to each other and form a line, because you could have some angles here that this is, let's say, 50 degrees, and you have a different angle over here that's 130 degrees. These 2 angles add up to 180, but they're not a linear pair. And then the last one, if angle 3 and angle 4 are supplementary, then they form a linear pair. No, that's basically saying the same thing here. These are supplementary, these are supplementary. They don't have to form a linear pair. The first one, if they form a linear pair, then they do have to be 180 degrees as well. All right, so definitely should be F on that one. All right, it says rectangle STUW is shown below. So I have the big rectangle on there. What is the length of ST? So I'm looking for this piece right here. All right, so I see there are some of the dimensions given, but not actually any of the dimensions of the entire rectangle. They're dimensions of, some pieces of triangles here. Conveniently, this is a rectangle, which means, though, that if I solve for like maybe one side over here, I can get the other one, or if I solve for the entire bottom, I would be able to use that same dimension for the top, because opposite sides of a rectangle are congruent. And that being said, as soon as I marked this side, I realized, oh, hey, look, I could actually solve for this side using Pythagorean theorem, because I know for sure on a rectangle that it has 4 right angles. So that is a right triangle. I could use Pythagorean theorem. Now, some students in the past I've seen attempt this problem just say, oh, well, why don't I just use Pythagorean theorem right here? Well, because what I just labeled, I don't know that that's true, and it doesn't even look like it's true. Is this a right angle right here? No. So you can't use Pythagorean theorem and just say 20 squared plus 8 squared equals ST squared, because I don't know that that's a right triangle. However, it is a rectangle, so I know all of the angles of the rectangle are right angles. So I'll go ahead and do this one first. I know that a squared plus b squared equals c squared. And this will be a and b. Let's call just that x for right now. Well, let's leave it as b. All right, so 5 squared plus b squared equals 8 squared. B squared equals 8 squared minus 5 squared. And take the square root to get 64 minus 25. So I get b equals square root of, what is that, 39? Yeah, 39. All right, so now that I know what b equals, that's one side of the rectangle. The other side also has to equal square root of 39. And as soon as I label that, I have two sides of another triangle. And if I solve for this one here, let's call this one A on this one, just so it's different from the last one. I know that A plus 5 is going to be the total side of that rectangle there, and it's going to end up equaling ST. So all I'll have to do is add up A plus 5 to get the whole thing. All right, so let's solve for A, add it to 5, see what we get. So I know that A squared plus B squared equals C squared. A is what we're going to be solving for in this one, plus square root of 39 squared equals 20 is the hypotenuse on this one, so 20 squared. So subtract subtract 39 squared from both sides. So 20 squared is 400. Square root of 39, they just cancel out. I get minus 39. All right, so it looks like I get 300 and what is that, 61? And then I think that that's going to be the value. Oh, if you circle that one, you made a mistake right now. Now that I know what A is, I need to add 5 to that to get my answer. So I guess I need to plug this in the calculator and then add 5. Square root of 361 plus 5. So square root of 361 is 19 plus 5. So then plus 5 should be 24. Yep, looks like we get 24 for that one. Tricky question. Yeah, we needed to add a plus 5 on that one. All right, number 18. For 18, it says statement given below. The number of square units in the area of a square is greater than or equal to the number of square units in the perimeter of a square. Which side of a square provides a counter, or which side length of a square provides a counter example to this statement? So the number of square units in a square is greater than equal to the number of units of the perimeter. So let's look at like 6. What does this mean? So if I have a square of 6, the perimeter, 6 times 4 is 24, and area, 6 times 6 is 36. So these would be square units. So now that we have this one, let's check and see what it was comparing. The number of square units of the area is greater than or equal to the number of units for the perimeter. The area is greater than or equal to the perimeter for this one. So I don't think that's true. When it's asking for a counter example, remember it is asking for an example that proves the statement false. This one didn't prove it false. This just confirmed what we guessed. So let's try 4 then. Same thing. We can draw a square, find the perimeter and area. All right, so 4. Perimeter equals 16. Area equals 16 units squared. So greater than or equal, great. But it is closer, and I got smaller. Let's try this one now, because perimeter will be 40, area will be 100. The area 100 is definitely more than 40. Let's try this one here and see what we get. 2, 2, 2, 2. Perimeter equals 8, but area equals 4. And the statement says the number of square units for the area of 4 is greater than or equal to the units for the perimeter, which is 8. Is 4 greater than or equal to 8? No. So this does provide a counter example, because this one proves that that original statement is true. The area isn't always greater than or equal to the perimeter. Number 19, the table below contains a pattern formed by the number of 6 of the Excuse me. Number 19, the table below contains a pattern formed by the number of sides and the measure in degrees of each exterior angle of several regular convex polygons. If the pattern in the table continues, which statement is true? So I see here as the number of sides increases from 3 to 90, so from a triangle all the way to a 90gon, the measure exterior angle measures. So the angle measures should be getting smaller and smaller and smaller. And that's exactly what's happening there. If the pattern continues, which statement is true? As the number of sides in the polygon increases by 1, the measure of the exterior angle decreases by 25%. Is that true? So 25% of 120 is 1/4 of 120 is 30. So it does decrease by 30 right here from 120 to 90. So on the first one it does, but let's check some other consecutive ones as the sides go. What about 90 and 72? So 25% of 90 is half would be 45, so 1/4 would be 22.5. This does not decrease by 22.5. That would be like 67.5. So this isn't true. It doesn't decrease by 25% every time. It just did on that first one. So I don't think it's that one. All right. The product of the number of sides in the polygon and the measure of each exterior angle is constant. So the product of the number of sides in the polygon and the measure of the exterior angle is constant. So when I multiply these, is that true? So what is 3 times 120? 360. 4 times 9, 360. 5 times 72, 360. Let's check the last one here. 90 times 4, 360. Yeah, product means multiply. If I multiply the number of sides and the exterior angle measure, so multiply this times this, I do get 360 every time. So that product remains constant. Pretty sure this is true. The measure C, we'll just to check this one to make sure, the measure of each exterior angle is a multiple of 6 degrees. That's not true. This is not, 8 is not a multiple of 6. The rest of them actually do happen to be from here forward, but these two are not a multiple of 6, so that one's not true for all of them. If the number of sides in the polygon is even, the measure of each exterior angle is a multiple of 3. So is that true? If it's an even number, the measure of each exterior angle is a multiple of 3? No, that's not a multiple of 3. That's an even number. So this one's also not true. So definitely going to be answer choice B on that one. Last one for this video. It says the volume of a rectangular prism is 960 cubic inches. If the dimensions of the base are doubled and the height remains the same, to create a new prism, what will the volume of the new rectangular prism be? So I know that volume of a rectangular prism is area of the base times height. And if it's a rectangular prism, then it's going to be area of the base is just base times height of the rectangle. So volume equals base of the rectangle times height of the rectangle times height of the prism. So it says if I have this volume and it equals 960 cubic inches on there, the dimensions of the base are doubled. Okay, so what happens if I double the dimensions of the base? So the dimensions of the base are the base and height of the rectangle. Let's double those. So what's the new volume going to equal? If I take the twice the base of the rectangle and I have twice the height of the rectangle, and then still multiply it by the height of the prism, because that didn't double. Well, if I multiply the values that I do recognize, because multiplication is commutative, order doesn't matter, I get volume equals 4 times base of the rectangle, height of the rectangle, and height of the prism, or 4 times the original volume of the prism. So if I double the dimensions of the base, I'm going to double the base of the rectangle and the height of the rectangle, and I'll get 4 times BR times HR times height of the prism. Or this represents the original volume, the original 960. So the volume of the new prism is equal to 4 times 960. So 4 times 960, let's check that real quick. 4 times 960 should equal 3840 for the answer on this one. So 3840 cubic inches. All right, see you guys on the next video. Let's do 21 through 30.